So let's record and then share my screen, which is this one. Okay. Okay, so let me draw again. I requested for anyway. I have requested for the paid Zoom, but still it didn't give me. So X, Y, and Z reference frame. And then you have, let's do another reference frame. I wish you would also provide me with that pen to easily write. Okay, U, V, and W. Okay, so now if we, I want to show the negative side to be in the, like this, so we can somehow understand it better. Okay, then you have this green one. You have also the negative axis on this side and the negative axis. And that's okay. So they're rotated. So here we say that we have the same, they're coincident here. Okay, so I hope that's clear now. And this is 60 degrees. If that is 60 degrees, that means this is 30 degrees. Okay. So the same thing here, this is 60 degrees. And the other side is 30 degrees. Okay, I hope that's clear. So now we are saying that there's a vector A and B that are expressed in terms of the X, Y, and Z frame. So we have A, let me just write A, okay, in terms of X, Y, and Z. And you have another vector B in terms of X, Y, and Z. So now we used to multiply it with that rotation vector. So now why is it that, oh, this is not the one. This one. So we used to multiply. In the previous exercise, we are saying that we multiplied to compute X, Y, and Z of A from U, V, W is equal to rotation matrix of X, Y, and Z into U, V, W multiplied by the vector A expressed from U, V, W frame. Okay, so now we are saying that instead of exactly the same rotation, we take the transpose of that rotation matrix. So the transpose of this, we use it here. So we say that in order to get for us the UVW of A from X, Y, and Z, we use the same, okay, X, Y, and Z are of UVW, then we get the transpose. Okay, Y wow, Y You pretend to have something wrong with your earphones and suddenly you have problems with your system. Mr. Guaho. Can you say something? Ramukati. Okay, yes. Continue. Yes, yes. Oh, what's wrong with him? Okay, Obakeng, can you stand for Boaho?
So I think we were supposed to use the rotation matrix Q instead of R. So Q relates to R, where at the Q is equals to the transpose of R or the inverse of R.
Okay, but is this correct?
Yes, sir.
Yes, because now what is equivalent to this one? What is the equivalent computation? The equivalent computation is what? So here, when you take the transpose, that's the same as saying that we are taking the X, Y, and Z of R, U, V, W. When you're taking the transpose, the same as saying that you're taking the inverse, right? It's my handwriting is so different. Okay, so here that R, you take the inverse. They're the same. Okay, so what does the inverse, when you take the inverse of rotation means? It means that you are changing the reference frame to the other. You're flipping the reference frame. So now you are doing U, V, W of R into Y, I mean X, Y, and Z. That means from X, Y, and Z, you're changing the reference frame to U, V, W. So now you have X, Y, and Z of A multiplied that vector. So you will get the resulting A from X, Y, and Z now becomes U, V, W. Okay? Okay? So, well, it's just a very simple computation, but I want you to understand the reason for the transpose is because we are using exactly the same rotation matrix, but we are flipping the reference frame. Okay? Okay, I hope that is clear. Okay, let me say goodbye to my drawing. It's so... Okay, now let's go to composite rotation matrices. So we already know how to change the rotation or the orientation or the reference frame of a vector expressed in one frame into another. And so the other way around, flipping the reference frames as well. We know how to do that. Now, but that rotation that we did was only simple, basic rotation matrix. A simple rotation about the z-axis. Now, oh, I forgot to record. Am I recording? Let me check by stopping. Let's stop the sharing first. Am I recording? Stop sharing. Yeah, I'm recording. I'm recording. Okay. So now let me share again. So if you go now to composite rotation matrix, so what does it mean is that, okay, can you please read, Musa?
Example, find the resultant rotation matrix that represents a rotation of theta angle about the OY axis, followed by a rotation of theta angle about OW axis. followed by a rotation of alpha angle about OU axis. Solution.
Okay, yes, read. Can you read, Musa?
I must continue with the solution.
Yes.
R is equals RY, comma theta I3 RW, comma theta RU alpha is equals to RY, comma theta RW,
It's not theta.
theta RU alpha.
The phi.
Huh?
Phi. The first the Greek letter, the first Greek letter is a phi, not a theta.
It's a phi.
Phi. Okay.
Okay.
Okay. Anyway, yes, that is correct. But before we continue, I want to tell you one important information. That let me do that drawing again. This file here. Okay. So there's one thing that you should know: the way we compute when we do composite rotation matrices. So composite rotation is again when you have several rotations happening in sequence. Okay. So first we say that, let me draw. In this composite rotation matrix, there's a rotation of a phi angle by OY axis. So the OY axis normally in the convention here that's being used is that initially you have your X, Y, and Z axis. Okay, that's your reference frame. So here it starts with an OY axis rotation. Here OY axis rotation of an angle phi. Okay, so that means if you rotate there, your X will rotate somewhere. Not yellow. Your X will rotate somewhere here. That will be your new X, which is now becomes a U. Okay. Normally, here the convention that is being stated here is that once you rotate the axis, you don't maintain the name X, Y, and Z. It becomes a U, V, and W, just to say that it is a rotated rotated axis. Okay, so it becomes U, and then the Z axis also. Okay. So the negative axis is over here, and then the Z axis will also rotate. Becomes in this case U, V. The V will remain here, and the W will be here, and then your W will also have the negative axis there. So let me do this negative side, and this one is also negative side. Okay, so that's how you rotate. So that's the convention. When you rotate, the new axis will become U, V, and W. Now from that new V and W axis, now you're going to rotate a theta of angle about OW. Where's OW? Now this is O and W. Okay, let me write it properly. Okay, so now we rotate OW axis. So OW axis is like that. Okay, so you rotate by an angle theta. Okay, so when you do that, that means that which one now is rotating? These two axes will rotate. This will also rotate. This will also rotate. So now there's a third axis now that one rotates. So your V will become somewhere here. I mean your U. okay, because that's rotated. And your W remains the same because that's the axis of rotation. And your V will also rotate somewhere here. Okay, there. Okay, so with that one rotation and the second rotation, and then the third rotation is OU axis. Now, OU axis, this one, it rotates again in the positive direction. Sorry, everything is in the positive. I'm doing negative rotation here. They're saying, let's just use all the positive rotations. So the brown one is a positive rotation according to the right-hand rule. So it should be like this. That's the right-hand rule. And then the W axis, also the right-hand rule. The thumb should point in the same direction as the arrow. That's the right-hand rule. And then the blue one, the U, you're going to rotate also right-hand rule of how much angle is it? Alpha. Okay. So those are rotations. Okay, now the convention that we're going to use here is that when you rotate, okay, if you rotate into the next, when you rotate from a reference frame to rotate to the next rotated frame, then you post multiply. You post multiply the rotation matrix. Okay, so we say here, then when you rotate from the initial frame into the reference frame, which is the X, Y, and Z in this case. The reference frame is X, Y, and Z, which is not the rotated frame. Then in that case, you pre-multiply. So this is, okay, let's just concentrate first on the post-multiplication. So we say that we rotate from, there are three rotations. So you rotate about Y. So you rotate about Y. Okay, let's just put the angle now so that there's less confusion. And then you rotate about W, the second rotation, and then you rotate about U, the third rotation. Okay, so now we say that when you rotate with respect to the reference frame, we will do a pre-multiplication. But in your rotate, if the rotation is from the reference frame towards the rotated frame, then it becomes a post-multiplication. If you can see here, there's an identity 3. Okay. So the reason for that is initially the axes are identical to each other. There's an identity of X, Y, and Z. And then when you rotate with respect to this reference frame, the stationary frame Y, then you will have to pre-multiply. So the I was here, you initially an identity, so you post-multiply the Y, the rotation about the Y axis. Okay, that's the convention that's stated in this work. But anyway, I will tell you later just some rule of thumb that will help you. But for now, let's accept that. Okay, that when you have the identity frame, okay, identity reference frame, and then you rotate with respect to that reference frame, we say it is stationary, and then it will be post-multiplied. I mean pre-multiplied. Then afterwards, we rotate into the rotated frames from the X, Y, and Z frame into the rotated frame. So you rotate from W, you rotate W from OW into the new rotated frame. Okay, so here you rotate OW by theta axis. So this rotation about the W, about the theta axis, will be post-multiplied because it's a new rotated frame. Okay, and then you rotate again to a new rotated frame, you post multiply again. You post multiply, you post multiply, and you post multiply again. You understand? Okay. With that, there's always like the formal definition, and for me, I always have my own way of understanding to help me better understand things. So always, okay, maybe it will help you also. Always, there's always a rotation from one frame to the next frame, right? So when you rotate from one frame to the next frame, so you always rotate. Forget about this pre-rotation, okay? You forget about this part first. You say when you rotate W to the next frame, okay, it will always be post multiplication. Whatever your status now, you post multiply with a rotation from that axis to the next. Okay, from that frame to the next frame. Okay, so now we'll always say that if you rotate from one frame to the next, then you always post multiply. So whatever your status now, whatever your rotation now, whatever this term is, you always post multiply because you go into the next frame. You rotate onto the next frame. Now you rotate again into the next frame, you again post multiply. If there's another frame that will rotate again after that rotation, you post multiply and keep on post multiplying. So when do you pre-multiply then? When? If you rotate and post multiply, rotate and post multiply. So when do you pre-multiply? Well, using the same information here, you keep on post multiplying, right? For example, there's another R of V here, yeah. Okay, that will also we will post multiply. Let's say that there are many rotations, yeah. So there are many rotations that you have to rotate here, RV, another rotation. We say another rotation R of W, whatever, the second rotation W, and then another rotation R of V, second rotation. Okay, so you keep on post multiplying because you have many rotate again. After rotating here, rotate on the next one, then post multiply, rotate again, the next one you post multiply. Okay, but if you can see this pattern, it means that if you move from here, okay, that means that if you were moving only from here to there, you keep in post multiplying. So, but then there is this process that the rotation of R of U is actually pre-multiplied with RV. You understand? You keep on post multiplying, yeah, because you rotate to the next rotate to the next reference frame, you post multiply. You rotate to the next frame, you post multiply. But in the process of post multiplying, you can see that actually RU is pre-multiplying RV. Right? You see that? This is pre-multiplying RV. So that means that rotation, okay, you pre-multiply it when you rotate from a reference frame. Okay, when you rotate from R, when you rotate from R to V, okay, when you rotate from RU to RV, but your reference frame is not the RV. It remains into the RU. You. Okay. Okay, maybe the easier way to also look at it is that where is the stationary frame and the moving frame? Okay, if you rotate with respect to, maybe this is easier. If you rotate with respect to the stationary frame, then you pre-multiply it. Okay, if you say, okay, for example, maybe in this case, maybe let's just assign 3 reference frames. Maybe it will be clearer. For example, you have 3 reference frames. Of X, Y, and Z. And then another reference frames that let's just separate them so that we can clearly see it. Another reference frame that's rotating, that's rotated. Okay, this reference frame UVW is rotated. Yeah, UV. Okay, so this is rotated to there. Okay, from X, Y, and Z, you rotate, for example, the first rotation. Okay, let's just say R1. Okay, and then now you rotate again. You rotate that. After you rotate, and then now you have another. Oh, I don't want to use green. You rotate, and then you have another reference frame. Let's just call it a different name. Okay. Why is it looking like that? Okay, it should not align. Okay, there. So in this case here, maybe R, S, and T are there's an R already. We call it F, G, and H. Okay, so there. So when you rotate, now you rotate R1. Okay, so when you rotate from here, rotate from X, Y, and Z into UV, and W, that's a rotation of R1. Okay, and then you rotate from here to here, from frame, let's just say this is frame 0, frame 1, so it's easy to say, to call them, and this is frame 2. So the next rotation, you post multiply it with R2. Okay, so now if you have another rotation, okay, and this is frame 3, then you rotate and there's a frame 3 times R3 here. Okay, so I think you get the idea now in terms of post multiplication. Okay, but the pre-multiplication is the question. Okay, so that means, so when do we pre-multiply then? So for example, if we are rotating, we'll just consider these things here, and we cover this part here. Let's say I'll cover it. I will cover it with another. I cannot cover. It's on top. Okay, anyway. So if we move, if we it's another 10 minutes. Okay, if we move from here to there, it is a pre-multiplication. So now, but then we say that because this frame moves with respect to this frame. Okay, in this case, this is the reference frame. We call this is a stationary frame, and this is a moving frame. Okay, if we say, okay, if this one happened later, we say that we rotate from frame 0 to frame 1 by R1, and then this is given. So we say, when we say we rotate from when we want to rotate from the reference frame, the stationary frame, into the rotated frame by R1, then we say that we have to pre-multiply it, because in this case, when you say the sequence of, maybe like this, with the sequence of rotation, then it will always be post-multiplication in this process. Maybe that's easier. Okay, you just see the sequence of rotations, and then we post-multiply everything. Maybe it's easier to just draw all the rotations, and then using the sequence, then you know which one is being pre-multiplied and post-multiplied. Pre-multiplied meaning multiplied before, and post-multiplied, multiplied after. In this case, we always post-multiply, because that is the sequence. We pre-multiply because here, this is the first sequence, of rotation. So in this case, this R1 is pre-multiplied by, is pre-multiplying R2 because it is the first sequence of rotation. Maybe that is the case. In this case, maybe it's easier to understand. Okay. So what I wanted to emphasize is that the order of multiplication matters. So you just make sure that you post-multiply according to the order of rotations. Okay. And then pre-multiply will be determined based on that sequence. Okay. Maybe that's easier. I hope it is easier. Let me remove all the annotations. Okay, let's continue. Now, so this is just an easy multiplication. Okay, I don't think I have to discuss it more thoroughly, because we know that post multiplication, if those things happen, then we just post multiply the rotation matrices, and these are the corresponding values. Okay, and then the resulting rotation matrix is this, by just multiplying those matrices. So this is the nice thing about the matrix rotation matrix multiplication, that now instead of drawing them on the paper, and sometimes our imagination, we cannot draw them properly, we commit mistakes in the drawing, so we cannot draw the projections correctly. We cannot compute the projections correctly. But if you're just dealing with matrices with purely numbers, all you need to do is to compute, and without even knowing, without even considering that maybe you have without trying to stretch your imagination and computing what could be the numbers using geometry. So in this case, you are just using numbers multiplication in matrices, and now whatever is the result, that is already the resulting rotation matrix. You can verify it with geometry, and but that is only the process of verification, not in the computation itself. But computing geometry can be that difficult. Okay, so next, this is a rotation using arbitrary axis. In this case, it is the principle is using geometry, but you will see that it can be helpful in terms of computing a rotation for any arbitrary matrix. We say that there is for any arbitrary vector, we say that there is a vector in space. Okay, this vector R in space, we don't know how is this R oriented with respect to this reference frame X, Y, and Z. Okay, so how are we going to represent this rotation in space by using our basic rotation matrices, rotation about X, Y, and Z. Okay, so the question now is, we always use the basic rotation matrices now, because that is our way of knowing the resulting matrix by using basic rotations and then pre-multiplying them until you reach to the final destination. So you reach the final rotation. For example, in this case here, let's check. So here we say that this is a vector and we want to rotate about this vector by some value. We don't know, by just some arbitrary value. So what we do is that we will rotate this R. We will bring this R to coincide with the Z-axis and rotate there and bring it back. Again, I will say it. What we will do here is that we will bring this R to align with the Z-axis, okay? Rotate there and then bring it back to where it was. Okay, so when we do that, it is equivalent to saying that we rotated already about the R-axis. You understand? So the process of bringing R to align with Z-axis, when we try to bring it back, that process is canceled. And what is remaining is just the rotation only, which will be equivalent to the R rotating around its own axis. Okay. Okay. So let's see how it is being done. So the first process R, this is one. The R goes here. So it rotates about where? It rotates about the X, this axis. Maybe let me. It rotates about that axis. Okay. That is positive. Okay. Is this positive? This positive. How come it's negative alpha? This part. Okay. Okay. I think this is the part. Okay, let's check. So positive. Okay. Rotate about the x-axis. Okay. Positive alpha. And then afterwards, you rotate about the V or the y-axis. Now this is a rotated axis. The V-axis, you rotate. Now the other way, so it's a negative. So this is the negative alpha. I mean negative beta. With the second rotation. We'll discuss why it is being post-multiplied. Then now here we rotate about the z-axis. Rotate about the z-axis. That's positive. That's positive phi. There's a second one, first, second, and then there's the third rotation. Okay. Then we go back. When we go back, we go back to the we go back to here. So when you go back, that's a negative beta. Or it's a positive, there's a positive beta. It's a fourth rotation because by right-hand rule, this is positive because your thumb is going up. Okay, number 4, this is the one, number 4. And then now here it will go up. When you go up, it's the other way around in that direction. When you go up, it's a negative alpha. Negative alpha. Negative alpha, that's the fifth rotation. Okay. Okay. Now the question. Okay, so we are okay. We are okay in terms of the sequence. I think we just follow those sequences, and then somehow this rotation is being canceled by this rotation. Okay, that we are remaining with somehow equivalently canceled, not physically like they're being canceled, but the effect is somehow canceled. Now we have the rotation matrix about the x-axis, I mean the z-axis. Now it's like rotating an arbitrary rotation of phi.